Swayam Prabha. Digital India. Educated India.
My name is Pradesha Ashok. I am an assistant professor at IIT Bangalore, and for the next 3 or 4 lectures, we'll discuss algorithm techniques. So, how many of you have done already done a course on design and analysis of algorithm? I think almost all of you, right? So, this is like more or less like a recap. At least this lecture will be a recap of the design techniques, which I'm sure you have already seen, but we will or I'll try to do it more rigorously. And the next lecture again we'll see which will happen tomorrow. Again we will see some graph algorithms and followed by some advanced techniques. I'll try to of course we'll cover randomized algorithms, also try to include more techniques like approximation and exact explanation. Okay, so start. So as I said, this lecture will be about algorithm design techniques. Broadly, we will cover 3 techniques which are the most popular among polynomial time algorithm, which are divide and conquer, greedy and dynamic programming. So we'll start with divide and conquer algorithm. Okay, so divide and conquer algorithm, how does it work? Yeah, since you have already seen, yes, right? Okay, so you are given an instance, you will divide the problem instance into 2 or more. Essentially, the idea is you will divide it into a small number of sub instances which are disjoint usually, and solve these instances. How will you solve them? Using recursion. Okay, so all of you know recursion, principle of mathematical induction and all that. Okay, fine. Okay, so you can smaller instances using recursion and combine the solutions of the smaller instances. Okay, now you have solved the smaller instances, you have the solutions for them. What you need is the solution for the actual bigger instance, and to get that you will combine the solutions of these smaller instances in some way based on which problem you are solving, and that is what happens. That's what happens in divide and conquer. I'll quickly give. I know you already know this example. It's merge sort. So merge sort, again, what is the input? An array of n elements, an arbitrary array, and you need the array in sorted order. Okay. So how does it work? Merge sort, like, okay, so it's divide and conquer, so you have to decide how to divide the array. So let's divide it into 2. Okay, so any way you need, but let's say that we'll take the first n by 2 elements as the first sub problem and the next n by 2 elements into the next sub problem. So we have 2 sub problems. We solve it. That means we sort it. Recursion will take care of it. Okay, right. So we solve it recursively. Now what do we have? We have sorted the first half of the input and the second half of the input independently. So what remains? You want to merge them into a single sorted list. That's what you need. And how do we merge this? So this is the conquer step. So these 2 are sorted. So what can you say about the minimum element in the merged sorted list? What will it like? It should be either here or here, the first position of one of these lists, right? That you can prove. Okay, so you compare these 2. Actually, it was supposed to be an animation. Fine. Okay, so you compare these compare these 2. 1 and 2, and whichever is the smaller of them should be the smallest element in the array. So you copy it here. Okay, So then you have a pointer which points to the element that you are comparing in for both the arrays. You move that pointer to the next element. Okay. So now the pointer is at 4 there and 2 here. Okay. So whichever is the smaller, again you move to the second position. Okay. And so on. I don't have to explain it much. I'm assuming you have already seen it. Okay. So this is the conquer step here. Okay. So yeah. So yes, of course you're using recursion. So the base case is when array is trivial, when array has only one element, you just return it. And the next step is you sort take the first n by 2 elements, sort it recursively, and take the second n by 2 elements, again sort it. And the third is the call to merge. That is the function that merges those two. Are you able to see this? Okay. So yeah, so we have this P and Q are the 2 pointers for the individually sorted sub-arrays, and at each stage you move the smaller of them to the merged. So what C is a merged list. So you move the smaller of them to the merged array and move the corresponding pointer. And once you are done with one of the arrays, like when you are finished, when you reach the end of one array, you just copy whatever is remaining in the other array to the merged array. Okay. Okay. So the correctness for this, why is this algorithm correct? How does it? How can you prove this? You can prove by induction that A1 and A2 are correctly sorted, right? Okay. And merge is correct because, yes, because of the reasons we said now, like for at every point you are comparing only two possible options for the next element in the merge array, and since you are taking the minimum of both of them, that should be correct. Again, you can prove it rigorously by using something like induction. Okay. Oh. So correctness done. What is the running time for this algorithm? How do we get n log? Okay. So so we are given an input with n elements. Let T of n is the time taken by merge sort to sort it. Okay, that's what we have to calculate. Then in here, what is the time taken for the second and third step? T of n by 2. So you have two recursive calls. Each will take T of n by 2. And after that, what is the running time for merge? How can you explain that? So yeah, you have an iteration, you have a loop, the while loop. So in the loop, they have a constant number of steps. So essentially you want to calculate how many times you call or how many times the while loop executes. Okay, so at every iteration we can observe that an element is added to the merged list. Okay, so how many items? So essentially the running time will be size of the merged list. So once an element is added to the merged list, you are not deleting it or you are not coming back to it. Okay, so this will give you the running time of merge as the order of size of merged list. Okay, so therefore this is order of n. So the total running time for merge sort will be T of n given by 2Tn by 2, which is the recursive calls, plus the time taken by the merge function n. And yes, this will give you order of n log on solving it. Of course, there is a base case. Okay. So that is divide and conquer. You can read on more algorithms which use divide and conquer. I don't think we are going to see much. Okay. So yeah, good. So now we'll go to the next topic, next design technique, greedy algorithms. So how does greedy algorithm work? What is a strategy used by greedy algorithms? Optimum solution is what you are looking for. Local optimum. Okay. right? But okay, so basically the idea is you take you start with the instance, or you see like a particular part of the instance, and choose an element from the input which looks locally optimal. I said looks or locally optimal because it is not clear, like when you say optimal or locally optimal, how do you compute it? It's not clear. Okay, so yes, at each step of the algorithm, okay, we'll call this a greedy choice. Okay. So why greedy? Because it's the current best, looks like the current best. Okay. So something that locally optimizes the solution by some measure. So these algorithms, greedy algorithms in general, they are the intuitive algorithms, but sadly the greedy intuition may fail also. So for designing greedy algorithms, one important part is to how to prove the correctness of the algorithm. So it is very important because you are working on greedy intuitions, which might not be very like not be easy to say that it will give you the actual optimum or the global optimum. We'll take an example here. So interval scheduling problem. So what is interval scheduling problem? Try to solve this using greedy. So intervals, what is the input? They are given n intervals on a real line, and find a maximum cardinality subset which are pairwise non-intersect. Okay, so you are given a family of intervals. Let's say an interval is denoted by or represented by its starting and finishing point. So every interval I, okay, I be the family of interval, and in interval here is defined by the start point. It's a closed interval, considering closed. The starting point and the finishing point of this. Okay, so this is the input, and what do you need to find out? A subfamily or subset of this set of intervals which are pairwise non-intersecting. So you cannot choose two intervals like this. Like once you choose this, you cannot choose this second because they have a common, they have an intersection. Okay, so you need to choose a pairwise non-intersecting, or what how we call as an independent set of intervals, and more or less we want to maximize the size of that. Okay. Okay, so and we are going to use greedy technology, greedy algorithms. So right, so we are given this input, and our idea is, or in general, how greedy algorithms work is like this. You select a greedy choice. We don't know how to select that, but you somehow decide on that and select a greedy choice and add it to the solution. Then convert the problem into a subproblem of smaller size. What I mean by, okay, for example, in this case, so here you are given an instance, let's call this I. So you choose your first greedy solution or part of the solution somehow, okay, and then what can you do? So you know that once you include an interval, you cannot take any interval that intersect with it, right? Okay, so you can delete all those intervals. Suppose this is the one I have taken, I have decided to take. Then I will delete all the intervals that intersect that, and also that interval. I have already added it to the solution, right? Now what is the rest of the problem? How do you get the rest of the solution? I can delete all these whatever I stars there, okay, and I take a new family like this and find the maximum sized independent set in that. So the problem is, how will you find, or what is the correct first greedy choice or the greedy choice that you want to take? Okay. So, any thoughts? You already know, huh? The longest interval? Someone said. Who was that? Okay, let's start from that. But I don't see the intuition for taking the longest interval. If you take the longest interval, then you can take, you cannot take many more, right? You have already covered a a space or a long length by just one interval. So, the one that finishes first. We'll come to that last. Okay. Okay. Right. The opposite of what someone suggested. Start with the short interval. At least you have the intuition that okay, I take a smaller interval. Now I have more space to fill. Maybe I will be able to take more intervals. Okay. So will it work? Okay. So you are given an intervals. So what I am suggesting is select an interval with the smallest length and continue. So what you mean is something like this. But here anyway there is only like one solution. Right? You can take only one of them. You take any of them, like this is a good case for us. There's only one solution is one here. So okay, so we'll taking the shortest one work. Okay, so if you believe this will work, we'll try proving it. Otherwise, we'll try to find a counter example where it will not work and move on. So if you have something like this, here the maximum independent set is these two, but once you take this one, you cannot take any more. So you have something that will not work. Okay, and yeah, more. Select the interval that starts first. Intuition is okay, like you start early, maybe you'll be able to do more, or maybe you'll be able to select more. Will this work in all cases? For all cases? Okay, why? Okay, give me one case where it won't work. Yes, right. So you have maybe something like this. The one that starts may go longer. Yeah, shortest we have already done. Third, select the interval with less conflicts. You know, conflict means the number of other intervals that this interval intersect. Again, intuition is okay. Once you choose this, you are not eliminating a large number of intervals. Okay, so maybe you so if you have a larger set, maybe you'll be able to choose. Okay. Okay, this looks like more, at least this intuition looks more convincing. Okay, so where is, suppose it won't work. So what is one case where it won't work? Rest will be very long. No, why is here the smallest conflicting is this actually. This is a good case for us, for this algorithm. The longest one, which okay, longest in itself is counterintuitive for me. Okay, less conflicts, fine. You're suggesting some new. Oh, okay, okay, okay. We are just. Yeah, the idea behind the counter example is like the maximum independent set may have a large number of conflicts, but can still be the maximum independent set. So for example, here this one has the minimum conflict. So you take this, once you take this, you can take at most 2 more, whereas 4 is the come to the what he suggested. Select the interval that finishes first. Okay. So you suppose you take an example like this. Okay. So select the interval that has the smallest finishing point. So here you will start by selecting this and you delete this. Okay. And which one will you select next? The smaller one, this. Okay. Then you have to delete this, and that's okay. And then you choose this, delete this, choose this. Okay. So you get 1, 2, 3, 6. Looks like the maximum independent set, at least for this example. Okay, right. Okay, so this is the algorithm that we are proposing. Okay, right. Okay. So yeah, we start with R is a set of intervals that we are processing at any point. A is the solution set we are building. Then while there are intervals in R, select the interval with the smallest finishing time, add it to the solution, and delete the intervals that intersect with the selected intervals and repeat with whatever remaining, if there is something remaining. Okay. Okay. So you want to prove that this is correct for all possible families of intervals. Okay. So before going to the proof of correctness, what will be the running time of this algorithm? So you want to find minimum of something. Minimum can be found in order of n time. And also for a given interval, you want to select the other intervals that intersect with chosen interval. How much time will it take? Okay, brute force, you are comparing everything with n square. And okay, so this was one step in the loop, and the loop will run for n times, right? Like order of n at least. Okay, it looks like, okay, this is a very loose counting here. We are looking at an n cube algorithm, but we can optimize the running time, right? How? Sort what? Finishing time. Okay, sort by finishing time. So it's kind of a pre-processing. Sort all intervals by their finishing time. Then this step, finding the smallest finishing time, will you can do it in order of 1 time. Okay, and how will you find for a given interval I? How will you find the intervals that intersect them without doing without comparing with every other interval? So are you going to compare take every interval and compare the starting? So you have sorted it with finishing time, also sorted by start time. Okay, so you have 2 lists. So once you have the starting time in sorted order, you take 1 by 1 and delete it till you find your starting time, which is the finishing time of I. Okay, then stop. So you are like, you don't have to compare with every interval. You have to take the intervals in the sorted order starting point and right. So if you do a pre-processing, that is sort by start time as well as finish time of the intervals, then this loop takes, or every iteration of the loop takes only order of 1 time, constant time. So the total running time of the loop will be order of n, but you are sorted, right? So sorting will take n log n. So the total running time will be order of n log. Okay. So now the correctness. Okay. So one way to prove the correctness of greedy algorithms is this. Of course, there are others. Okay. First step is prove the solution is a feasible solution. What do I mean by a feasible solution? The one, like for example, in this case, the feasible solution is a family of intervals that are pairwise non-intersecting or that are independent. Okay, first prove that. And once you prove the feasibility, then you have to prove the optimality. That is, you want to show that the set of intervals is the maximum sized or the largest cardinality of independent. Okay, how will you prove that? So to prove this, one technique is this: take any other solution, take any other feasible solution, and prove that you can transform our greedy solution, transform this solution into a greedy solution. That is, you can change the solution, let's call it S. Okay, you can change a solution S in steps so that it becomes exactly equal to our greedy solution. Okay, right. We'll use this technique here to prove. So here what we do is, okay, so we have a greedy solution obtained by choosing the interval that finishes first. Okay, so let G be that solution. So let's say this is my greedy solution. Okay, and so on. Now I take any other solution, any other feasible solution. Okay, it can like look like this. Okay. So I'm going to convert S into G without changing the quality of S. What do I mean by that? Is by quality I mean the function that we are trying to optimize. So S will have, so in this case, what will be the, how will you measure the quality of S? Cardinality of S. So you are not, while in this transformation process, you are not reducing the quality of S, or in other words, you are not reducing the cardinality of S. Okay, right. Now here, so you have G and S, they are sorted by their start time, let's say. Okay, now look at the first place where G and S are not the same. Okay, so so these are same, this is same. Here, so this is the first place where G and S, or the corresponding intervals in G and S, are not the same. So what I will do is, I'll delete the interval from S and instead of that replace the interval from G. Okay, this is fine because, okay, so let's say this is my greedy solution. Okay, so before this, G and S are the same. Okay, so G equal to S in this part. Now I take, okay, I'll take let's say this is the ith position in J. I'll consider the ith interval in S. How can it look like? It cannot look like this. Why? Because then greedy would have chosen that, right? Greedy we had taken the least finishing time. Okay, so this cannot look like this. So this has to like look like either this or like this. Okay, so if you interchange this, if you swap this in S, it won't change the quality of S or the number of subsets in S, because you have deleted one, you have added one, and moreover it is, this will not, the new one, the GI will not conflict with other intervals in S. Okay, so you have changed it and you continue this process. Okay. And you can see that if you continue this, you can transform S into our greedy solution G, right? Okay, so in sum, without changing the size of S. Okay, So what have you proved? So you have proved that any feasible solution can be converted into a greedy solution. Does that prove that a greedy solution is the best possible? It sure does, right? You can convert any solution to a greedy solution. Equivalently, you can convert any optimal solution into a greedy solution without changing the size. That implies greedy is the optimal. Okay. Is that clear? So that is the proof of correctness. So for interval scheduling, there's selecting the fastest finishing or the earliest finishing interval will give you the optimal solution. So fractional knapsack problem is this: you are given a knapsack or a bag with capacity, let's say capital K. You are also given n items. For each item, you have two values. Wi is the maximum weight available of ith item. Like maximum weight available means okay, the maximum weight available to that can be packed into the knapsack. And for each item, there is a total cost, or like you can even think of it as a profit. Okay, so CI means this means if you pack the entire Wi, you will get a cost or profit of CI. Okay, and the question is to pack the knapsack with as many items as possible such that the total cost or profit is maximized. Okay, so something like this. Okay, so you have a bag. Okay, and in this version, you can even take a fraction of the total weight available. So like in this case, so you have given 3 items, one with 2 kg, 2 kg, 3 kg, and you have to pack them into a bag of capacity 4 kg. Okay. And if you pack the first item, the entire 2 kg of the first item, you get a cost or profit of 100. Okay, since it is fractional, like if you take only half of it, you are allowed to take a fraction of it. For example, if you are taking 1 kg of the first item, you will get a cost of 50 and so on. Okay, you want to pack these items into the bag of capacity 4 such that the profit is maximized. The total profit you get is maximized. So what will be one way to do is like, so for example, if you pack the first item and second item, you'll get a 110 profit. Or if you take the third item first, enter 3 kg of the third item, 120, and of course you cannot take 2 more. So you take, let's say, half of the first item, so you will get 170. Okay. So you have to find out which is the optimal weight. Okay. And what are the possible choices for your greedy? Yes. Yes. So this is what you are going to do. Choose the item with the largest value of cost per unit weight. We call it PI. So here find the values of PIs, okay, which is given by CI by weight, okay, and select the item with the largest PI. So what will be the solution now? Item 1 has the largest value of unit profit per unit weight. So you take, okay, how much to take? Whatever is possible of that item. Okay, so here you can take the entire, because you have a capacity of 4, you are taking 2. Okay, the entire 2, so you get a profit of 100. Okay, what is the next item to be chosen? Third one, right? Third one has the next largest PI, 40. Okay, but you cannot take the entire 3 kg because you have already chosen 2 out of 4 and you have only 2 remaining. So you take whatever is possible, like 2. So 2 kg of third item. So you will get a profit of Yes. Okay. So this is the best, or so we claim. Okay. Right. So the algorithm is this: sort by, okay, sort by the PIs, and okay. So running time, sorting takes order of n log n, and next is how much time will it take? Okay, you're taking considering one item in the loop, so loop will run order of n times. So total running time will be order of n log. And how you prove the correctness for this?